26,000 light-years from where you're sitting, in a cloud of gas and dust near the center of the Milky Way, astronomers just found sugar. Not a sugar-like molecule, not a chemical cousin. An actual 4-carbon sugar, the same compound that shows up naturally in raspberries, floating in interstellar space, light years from the nearest star, before any planet in that region has even had the chance to form. The discovery was published on July 13, 2026, in the journal Nature Astronomy, led by astronomer Izaskun Jiménez-Serra at Spain's Center for Astrobiology. Her team wasn't chasing sugar specifically. They were running one of the deepest chemical surveys ever done on a molecular cloud called G plus 0.693 minus 0.027, a dense pocket of gas sitting near the galactic center, roughly 8.2 kiloparsecs away. That distance converts to about 26,000 light-years, and it puts this cloud in one of the most chemically active regions of the entire galaxy. To find the molecule, the team used 2 radio telescopes in Spain, the 40-meter dish at the Yebes Observatory, north of Madrid, and the 30-meter IRAM telescope in the Sierra Nevada. Molecules in space don't sit still for a photograph. They get identified by their radio signature, a kind of fingerprint made of very specific emission lines that show up when a molecule rotates and vibrates in a particular way. Every molecule has its own unique pattern. To confirm a match, researchers first have to measure that exact pattern in a lab on Earth, then go looking for it in the noise of deep space data. That's exactly what happened here. The team compared their observations against a laboratory spectrum of a molecule called erythrulose, measured at the University of the Basque Country, and found 12 separate spectral lines that lined up. 12 is not a coincidence-sized number. It's the kind of match that lets a team confidently say, this molecule is really there. Erythrulose has the chemical formula C4H8O4, 4 carbon atoms, 8 hydrogen, 4 oxygen, 14 atoms total. On Earth, it's mostly known for 2 unrelated reasons. It occurs naturally in red raspberries, and it's the active ingredient in a lot of sunless tanning products, which is why some skin turns orangish if you use too much of it. In space, though, its importance has nothing to do with raspberries or tanning lotion. Erythrulose is what chemists call a ketose sugar, and it belongs to the same broad family of molecules that eventually build the backbone of RNA and DNA. Here's why this particular detection matters more than it might sound like at first. Astronomers already suspected that sugars existed somewhere out in space, because traces of them had shown up before. But only in solid material, not in a gas cloud. Sugar molecules like ribose and glucose have been found inside meteorites, and more famously, inside samples that NASA's OSIRIS-REx mission brought back from the asteroid Bennu. Those detections told scientists that sugars can survive inside rocky bodies. What they couldn't tell scientists is whether those sugars were made on the asteroids themselves, or whether they arrived already formed, drifting in from the interstellar medium before the asteroid ever existed. This new detection answers that question. Because erythrulose was found directly in a molecular cloud, not inside a rock, not inside a comet, but suspended in gas and dust in the space between stars. It shows that this level of chemical complexity can build up before any solid body exists at all. In other words, the sugar didn't need an asteroid, a comet, or a planet to form. It formed in the open, cold vacuum of interstellar space, on the surface of tiny ice-coated dust grains, using far simpler starting materials. There's a second layer to why chemists are excited, and it has to do with how molecules are supposed to grow in space. The standard model in astrochemistry says complexity builds up gradually, carbon atom by carbon atom, in a fairly predictable sequence. Jiménez-Serra's team found something that broke that pattern. According to the study, erythrulose showed up in far greater quantity than smaller, simpler three-carbon sugars like glyceraldehyde and dihydroxyacetone, molecules that, by the standard model, should have been easier to make and therefore more abundant. Instead, those three-carbon sugars weren't detected at all in the same cloud, despite a survey sensitive enough to have caught them if they were there in any real quantity. Erythrulose, the bigger and supposedly harder molecule to build, turned out to be at least 8 times more abundant than its simpler cousins. That number, 8 times more abundant and completely out of step with the expected order, is the detail that makes chemists sit up. It suggests erythrulose isn't built the slow, sequential way scientists assumed. Instead, the current best explanation is that it forms efficiently straight from much simpler 2-carbon molecules, alcohols and aldehydes, reacting together directly on the icy surface of dust grains. Skip a few expected steps, and you get straight to the 4-carbon sugar. There's one more detail that matters almost as much as the sugar itself. Erythrulose is chiral. Chirality means a molecule and its mirror image are different from each other, the same way your left and right hand are mirror images that can never perfectly overlap. Life on Earth is deeply particular about chirality. Our DNA, our proteins, our sugars almost all favor one specific handedness over the other, and nobody fully understands why that bias exists, rather than a 50-50 mix. According to the research team, erythrulose is only the second chiral molecule ever confirmed in the interstellar medium. Finding a second one, in a completely different cloud than the first, hints that handed chemistry might not be a rare fluke. It might be a normal outcome of how molecules form in space, and that connects to something a lot bigger than one cloud near the galactic center. If sugars, including chiral ones, can build up in interstellar gas before a single planet exists, then, when a young star system forms out of that gas, the raw ingredients for that kind of chemistry are already baked in from the start. Those molecules can get swept up into asteroids and comets as the system takes shape, and later delivered to young planets through impacts. The same way scientists think organic material reached the early Earth during the late heavy bombardment, a period roughly 4.1 to 3.9 billion years ago, when the inner solar system was pounded by debris left over from planet formation. Under that picture, some of the sugar chemistry inside your own cells could trace its lineage back past Earth, past the Sun, all the way to a cloud of gas that existed before either one did. Outside experts have been quick to weigh in. Brett McGuire, an astrochemist at MIT who wasn't part of the study, called it one of the results the field has been pushing toward for a very long time. Mark Sefton, at Imperial College London, pointed out that finding these compounds already present in interstellar space adds real weight to the idea that our own solar system was seeded with organic material before it even finished forming. And co-author Carlos Briones noted that this detection opens the door to finding other, more directly biological sugars out there, specifically ribose, the sugar that forms half of the backbone of RNA itself. It's also worth understanding just how unusual this particular cloud already was before the sugar turned up. G plus 0.693 minus 0.027 isn't some random patch of gas. It's one of the most chemically rich regions astronomers know of anywhere in the galaxy. Researchers have already cataloged more than 340 different molecules drifting through it. Everything from simple building blocks to some of the most complex organic compounds ever confirmed in space. Sugar was one of the last major categories still missing from that list, which is part of why this detection felt overdue, rather than out of nowhere. And there's a curious postscript to how erythrulose was found at all. The team's initial search wasn't even for a 4-carbon sugar. They went looking first for the simpler 3-carbon sugars, the ones the standard model said should be there. When those came up empty, the search for something with an extra carbon atom is what led them to erythrulose instead. The wrong answer to the original question ended up being the far more interesting one. To be clear about what this discovery does not show, finding erythrulose in a molecular cloud is not evidence of life anywhere in that cloud, and it's not evidence of life on any other planet. What it shows is that the chemical ingredients life eventually uses were already available, in surprising complexity, long before life, or even planets, had any chance to exist. The universe, it turns out, may have been stocking the pantry billions of years before anyone showed up to cook. Beyond what you can see, but never beyond what you can understand. Subscribe and check out the rest of the channel. New episodes on space, physics, and the edges of what we understand, with new content going up every day.